By far, the most common mistake on Mohr Circle stress transformation problems is going to be dealing with the angles at the end, how to rotate the stress element to find the principal stresses or the max in-plane shear stress. Don't worry, your TA Indiana and me, we got you covered. We're going to work through two example problems because you're going to get through the first one. You're just going to be like, whoa, this is a lot. I do not have it yet. So we're going to work through it again a second time. Once you see it the second time, then it's going to start to sink in. So left problem first. We're going to start off by taking our X and Y dimension loads, the 32 megapascals and 55 megapascals, plot those on the horizontal axis. The right side is positive 55, left side negative 32, since the negative 32 is in compression. Now we're also going to plot 2 points, which are going to be points on Mohr's circle. And these are going to use the 42 megapascals, that is the shear stress in the vertical axis. And positive and negative for shear stress are a little bit hard to define, because if you look at shear stress, one side it's pointing down and the other side is pointing up, and one side it's pointing left and the other side is pointing right. So what direction even is positive? So this is why I have labeled clockwise and counterclockwise. The below the x-axis is counterclockwise, up above is clockwise. So at my positive 55, if you look at that arrow that's pointing to the left, that is rotating in the counterclockwise direction. So I plot my point 55 down 42 to the counterclockwise side. But over on my negative 32 has the 42 megapascal shear going clockwise. That's up above the x-axis. So my point will be at negative 32 up 42 to the clockwise 42. So these are going to be used at the end of the problem when we start to solve for angles. But first, let's do some of the math here. We'll find the center of Mohr circle is just the average of the 55 and negative 32. So positive 11.5 center of the circle. Now radius of the circle, we'll just do this by drawing a triangle. It's just a Pythagorean theorem. The height of the triangle is the 42, and the base of the triangle is from the center to one of my blue dots. So from the center 11.5 to 55. So little Pythagorean theorem, square that. 60.47 is the radius of the circle. And the radius of the circle is also going to be the straight vertical height of the circle. So that's going to be your maximum in-plane shear stress, R. R is tau max in plane, 60.47. So the principal stresses will just be horizontal. So from the center, plus R or minus R will get us to the left and right sides of Mohr's circle. So 11.5 plus or minus 60 gets us to 72 and negative 49. Those are the principal stresses. Last thing we need to find using Mohr's circle is going to be an angle. And now the first weird part that students are going to mess up is that this orange angle that I'm drawing is actually 2 theta. And the reason for that is that half of a circle is 180 degrees. That is, if we go from one of our points to the other point, you rotate through 180 degrees. But when you're rotating a square, you only have to rotate a square 90 degrees before you've kind of flipped it. So from 180 degrees to 90 degrees, basically 2 theta on the circle is 1 theta on the square. That might make a little bit more sense in about 2 minutes when we actually start rotating the square. But for now, maybe just trust me. 2 theta is this angle inside here. So I'm using the same triangle that I used to solve for R, but now I'm going to say that tangent 2 theta is opposite over adjacent, where the opposite side is that vertical height 42, and the adjacent side is going to be this 55 minus 11.5, just from the center out to my force. So inverse tangent, get theta 22 degrees. So now the big question, how do I actually use this 22 degrees to rotate my stress element to describe these principal stresses. And now this is why we found those points at the beginning, this 55, 42. From that red dot, if I rotate counterclockwise back to sigma 1, back to the x-axis, back to the principal stress, what that means is if I take my square, my original stress element, and rotate it that same direction, 22 degrees in the counterclockwise direction, then that 55 megapascals that was on top, that is my point, that will now be pointing in the direction of P1, the principal stress one, the maximum principal stress, the one that's pointed all the way to the right. That was our 71.97. So then the other principal stress is in compression, the negative 48.97. And so this is by taking a 22 degree rotation counterclockwise, the 55 megapascals becomes 72. What about the direction of maximum shear stress, the maximum in-plane shear stress? The maximum in-plane shear stress would occur if instead of going counterclockwise to P1, I instead went clockwise down to T to tau in plane max, basically the vertical position. Instead of rotating up to the horizontal position, I rotate downwards to the vertical position. And so 90 degrees on the circle is actually 45 degrees on the square, right? It's angle over 2 theta. So instead of 22 degrees one way, it's 23 degrees the other way, right? It's a 45 degree shift. So if I rotate 23 degrees clockwise, this turns the 55 now to 11.5. And in fact, both directions are 11.5 because at the max in-plane shear stress, both x and y direction stresses are exactly the center of the circle, 11.5. But now, which direction do I draw shear? For my top flat surface, should shear be drawn pointing to the left or to the right? So my axes labels for this bottom point is drawn as counterclockwise. So since this 55 megapascals, it's rotated 23 degrees. So I'm looking at this top surface should also be drawn with shear stress pointing as if it were rotating counterclockwise. Or oppositely, suppose instead of looking at this 55, which is in the bottom right of Mohr Circle, suppose we were looking at the negative 32 that was in the top left of the circle. When we rotate that negative 32 up until it gets to the top, right, the max in-plane shear stress at the very top of Mohr Circle, at the top of Mohr Circle, shear is rotating in a clockwise direction. So my 32 that was horizontal, that's now rotated a little bit downwards from horizontal, that surface should have shear stress rotating clockwise, which is down on that position, which confirms that it makes sense and that we've drawn our shear stress in the correct orientation. And now I guarantee 100% you've gotten to the end of this and you've been like, what? Maybe I get it. But at the same time, I have absolutely no idea what's going on anymore. That's why we're doing 2 example problems. So we're going to start over. We're going to do this whole thing one more time. And I think maybe seeing it again will help it sink in a little bit more. So we start off, we draw Mohr's circle. Positive 18.4 on the horizontal axis, negative 13.1 on the horizontal normal stress axis. Center of the circle is the average of those 2 points. So positive 2.65 is the center of Mohr's circle. Now we're going to label our 2 points on Mohr's circle that we're going to need in order to solve for the radius. So the 18.4 has its surface, shear is pointing to the right, which is clockwise, which on Mohr's circle, clockwise shear is above the axis. So I'm going over 18.4 up to 27.9. And my other point, the negative 13.1, has its shear stress pointing upwards, which is causing the stress element to rotate counterclockwise. Counterclockwise on Mohr Circle is below the x-axis. So I draw my point at negative 13.1 down 27.9. And so I can connect those 2 points to draw a diameter of Mohr Circle. And that lets me then draw the full Mohr's Circle itself. So the radius of Mohr's Circle, right? I'm using basically just drawing a triangle here and doing a Pythagorean theorem. The height of the triangle is the 27.9. Base of the triangle is my 18.4 minus the center, 2.65. So square those, do a square root. 32 is my radius. And that radius is also going to be the in-plane max shear stress, right? The height at the top and bottom of Mohr Circle. My principal stresses are going to be the center plus the radius and the center minus the radius. So I'm going to positive 34 and negative 29 as my principal stresses. And then to find theta, this rotational angle, as to how far we have to rotate the original square to find these principal stresses, I'm going to redraw this orange triangle here. And remember that this angle is actually 2 theta. So tangent to theta is opposite over adjacent. So opposite is that vertical 27.9 shear stress. Horizontal is from negative 13.1 to 2.65. And this is going to get me an angle of about 30 degrees for theta, because the 2 theta is about 60 degrees. So cut it in half, 30 degrees for theta. Now, if I take this point that is at the bottom left of Mohr Circle, I'm going to need to rotate it clockwise to get to principal stress 2. So I'm taking my 13.1 that's in compression, rotating that surface downwards in the clockwise direction, and that new, after I've rotated it, that's going to be the negative 29 KSI principal stress. And so the other principal stress will be the positive 34.69. So if I took my 13.1 point on Mohr Circle, rotate it clockwise, that gets to the principal stress. And so by taking my stress element, rotating it clockwise 30 degrees, that is the orientation for principal stresses, and there's no shear stress in the principal stress orientation, only that max and min principal stresses. But instead, I could go 45 minus 30 degrees in the other direction. I can instead of going up to sigma 2, I can instead go to the maximum in-plane shear stress, which is the very bottom of Mohr's Circle. So if I take the original square stress element and now rotate it 14 degrees counterclockwise, that takes this point, this 13.1, 27.9, that point, and moves it down to the maximum in-plane shear stress. And so this 13.1 surface is now going to be 2.65. In fact, both directions will be 2.65 because at the max in-plane shear stress, both X and Y stresses are right at the center of the circle. They're both 2.65. So by far, the most common mistake with Mohr Circle is dealing with these angles, figuring out whether you need to rotate clockwise or counterclockwise, and then do you draw your shear stress pointing upwards or downwards or leftwards or rightwards? So it all starts from tracking those initial 2 points that you draw on Mohr Circle, and then keeping track of whether you need to take those points and rotate them clockwise or counterclockwise to the principal stress, and clockwise or counterclockwise up to the max in-plane shear stress. And then whether you have rotated it up to the top, where shear stress would be clockwise, or if you've rotated it down to the bottom, where shear stress would be counterclockwise. But this horizontal surface, the one that I have rotated up from 13.1 is now 2.65. That is now at the bottom of Mohr Circle. The bottom of Mohr Circle has counterclockwise rotation. So on that surface will be counterclockwise rotation, so that's going to be pointed upwards. And in fact, we can check the other side. Suppose we were looking at the opposite corner, the one that's on the top right side of Mohr Circle, the 18.4. If we took that surface and rotated it 14 degrees counterclockwise, we would now be at the very top of Mohr Circle. And at the top of Mohr Circle, shear stress is rotating clockwise. So our top surface, 2.65, should have clockwise rotation for shear stress, which fortunately that does. That perfectly matches what we expect it to be. So I know it's a lot to take in, but your TA Indiana believes in you. We know you can do it. Good luck on your next test.